You know, conservation laws are always associated with some symmetry in our nature. And when a conservation law is expressed mathematically, not all, but most of the conservation laws are expressed in terms of a first order partial differential equation, and that very equation is called equation of continuity. So, in this short lecture, we are just going to see what are the equation of continuity for different conservation laws. Actually, I have taken here, for example, most importantly, six conservation laws, and I have written the equation of continuity for those laws. Actually, all those equations represent conservation of some quantities related to that law. Okay. And one thing is also very important here, that almost all the equation of continuity have same mathematical form. So we will see in this short lecture that what are the equation of continuity for conservation of electric charge, of conservation of mass, conservation of distribution function, which we study respectively in electrodynamics, in hydrodynamics, and in statistical mechanics. And at the same time, you will also see the equation of continuity for conservation of probability, which you study in quantum mechanics, and conservation of momentum, which you study in classical mechanics, and conservation of energy, which is studied everywhere. But here I will write the equation of continuity for the conservation of energy, which is used probably in plasma physics, okay, or in transport phenomena. So let us see. When you talk about the conservation of electric charge, you know that the total charge of an isolated system remains conserved, and this conservation of electric charge is expressed mathematically by this equation given like this. This is divergence of J plus del rho by del T equal to 0. Actually, this equation is called equation of continuity, and this represents the conservation of electric charge. Here you can also write this divergence of J equivalently as del dot J, and you know this J is electric current density vector and rho is the volume charge density. Okay. Exactly, you can see when you talk about the conservation of mass, the total mass of an isolated system remains conserved, and this conservation principle is expressed by the equation of continuity written like this. This is divergence of rho u plus del rho by del T equal to 0. Here this rho represents actually mass density. It means this is mass per unit volume, and u is the average velocity. Okay. You can see that the mathematical form of these two equation of continuities are exactly same. Okay. Again, the conservation of distribution function in phase space. This conservation principle is expressed by the equation of continuity written like this. This is divergence of rho u plus del rho by del T equal to 0. You can see this equation is exactly same as that of the equation of continuity for conservation of mass. Actually, here this rho is known as a statistical distribution function, or it is also called simply distribution function or probability distribution function, or it is actually the density of phase point in phase space, that is number of phase point per unit volume of the phase space, and u is the velocity of phase point. So these two equation of continuity are exactly in same form, although the meaning of the quantities here differs, but the form of mathematical equations are exactly same. In quantum mechanics, we study a very important conservation principle, that is conservation of probability. Okay, whenever the probability of a system finding in a particular state decreases, definitely its probability in finding in some other region of the same space increases in same amount in same time. And so we say that the probability remains conserved. And this conservation principle is expressed by this mathematical equation, which is called equation of continuity. This is divergence J plus del rho by del T equal to 0. You can see that this equation is exactly same as that for the conservation of electric charge. But here this J does not represent the electric current density. This actually represents the probability current density. Okay, that is probability flowing through unit area in unit time. Okay, and this rho is not the charge density or mass density. This is called probability density. That is, it represents the probability of finding of a particle, finding of a system in unit volume. Okay, in unit volume. So this is the equation of continuity for conservation of probability, which we study in quantum mechanics. Okay. Now, conservation of momentum. Actually, this equation which I have written for the conservation of momentum, which is called equation of continuity for conservation of momentum, is actually best known as Euler's equation. Euler's equation is simply the equation of continuity for conservation of momentum, and generally we study it in hydrodynamics. Okay, and this equation of continuity is given like this. This is rho times del T plus u dot del u plus del P by rho equal to F by m. Here actually this rho represents the mass density, that is mass per unit volume, u is the average velocity, and P is actually pressure. P represents pressure. And when you say del P, then that will be gradient of P. So del P is what? This is gradient of P. Gradient of P. Okay. And m represents the mass, and F represents the net force acting on the system. Okay, so you can see that this equation, which is also an equation of continuity or Euler's equation for the flow of fluid or flow of any incompressible gas or liquid, which represents conservation of momentum, actually the form of this equation is slightly different from all the four equations which we have just seen earlier. Okay. Now, to represent the conservation of energy, particularly in plasma physics, when we discuss the problem of transport phenomena, then by solving the Boltzmann transport equation, we actually arrive at a result which represents the conservation of energy, and this equation is written like this. This is rho del T plus u dot del theta equal to minus 2 by 3 del dot q minus 2 by 3 p dot del. Here you can see that what are the different quantities. You can see here. Actually, here this theta represents the temperature. Okay, and this vector q represents the heat flux vector. This is heat flux vector. And see the symbol over P. Actually, the double arrow head over P is used to represent a dyadic. You know, dyadic is what? Dyadic is a tensor of second rank. Okay, you know that vector is a tensor of first rank and dyadic is a tensor of second rank. So this symbol actually represents that this P is a dyadic and its components are Pij. When you say Pij, that will be P if the space is three-dimensional. This Pij will have 9 components. This will be P11, P12, P13, and just like that P21, so on, and then P31, so on, P33. This will be the 9 components and so this represents a dyadic. Okay, and as you know that divergence of a vector is a scalar quantity, but divergence of a dyadic is a vector. So this del dot p is not a scalar, it is a vector whose ith component is given by del pij by del xj. Okay, but the scalar product of two dyadics is a scalar, just like ordinary geometrical vector. So this p dot del represents a scalar whose value is pij times lambda ij. So I think you have seen that the very well-known conservation principles are expressed mathematically in terms of a first-order partial differential equation, and almost all those equations have same form, and those equations are called equation of continuity. Okay, thank you very much.